Today we're talking about the San Andreas Fault, mostly because it's like one of my favorite things to talk about. I took a quick day trip up to the Carrizo Plain National Monument, which is located about 2.5 to 3 hours north of Los Angeles, because I thought it would be really cool to be able to show you guys one of the most iconic Southern California geology spots. So Carrizo Plain National Monument, when you see that image of the San Andreas Fault where it looks like someone dragged a knife through the earth, that's up at Carrizo Plain. In particular though, Wallace Creek is just, it's cool. It's a creek that has been what's called offset, so where it's been moved by earthquakes. And I'm gonna talk you guys through what it is, how it works, and just do some quick geology. First section of the San Andreas Fault is in the northern section. It runs from about Cape Mendocino, where it comes on shore, down to about Hollister, sort of just around that Monterey Bay area. That last ruptured in 1906, the Great San Francisco earthquake. The second section runs from Hollister south to about Parkfield, and it's super cool. It actually is the creeping section. We're not going to talk about it right now, but it's really awesome. The third section of the San Andreas Fault runs from Parkfield south to, a little south of Parkfield, south to through the Salton Sea, and that is the southern section. We first visited it with the Salton Sea videos. And then today I am at Soda Lake Road. So that's a little bit further north. It's north of what's called the Big Bend, which is where the San Andreas Fault bends. So this section of the fault last ruptured in 1857. That rupture went from Parkfield down to about Palm Springs. The southernmost part of this section hasn't ruptured since 1680. All right, what you are looking at here is we've got a stream channel that makes this really distinctive Z shape. So like that. And you've got one end of the stream channel running here in the foreground at the bottom of the Z, and then you've got one end of the stream channel up here at the top of the Z. You got some people right there that we can use them for scale, just so you can get a sense of how big this is. And what originally happened was that side and that side were connected like that. But then this little line right here, that would be the San Andreas Fault moving through and muscling both sides of it out of the way. The San Andreas Fault is what we call a right lateral strike slip fault. So what we're going to do is I am going to use this handy post. Post is the Pacific plate and I am the North American plate. So the camera is the North American plate. And what's going to happen is we're just hanging out and then all of a sudden there is an earthquake. I just yanked the dog, my poor dog. So what just happened? The post went from being in the center of the screen to the right of the screen. That is, when we say right lateral strike slip fault, it's because we're referring to the direction of movement relative to the side you're standing on. Fault is moving at about 1.5 inches per year, so that's about 125 feet per 1,000 years. So theoretically, if you were standing here at Wallace Creek, where we are, if you were standing here, what would happen is in about 10 million years, you would be up in San Francisco. But during that process of getting to San Francisco, it wouldn't be happening in slow movement. It would be happening through very, very violent earthquakes. Generally speaking, what you would end up seeing is displacement as you're standing there. You would be thrown into the air very high, but then you would also be moved anywhere between 10 to 30 feet at a time, which is how you get this kind of massive amount of movement on the plates and these catastrophic earthquakes. We're down here, you've got the creek there, it goes across. You've got the San Andreas Fault kind of running through here. To be clear, it's sort of a zone. This isn't necessarily the exact fault, but it is part of the fault. And then it goes off again in that zag over there. So what we also have, this is about 430 feet of offset. So this has been happening when we talk about these earthquakes happening. This isn't happening in one fell swoop. This is happening over thousands of years. So this offset has occurred slowly over time. What we also have is this here, which is what's called a fault scarp. We talked about fault scarps when I did the LA drive and went to the Capitol Records building. The Capitol Records building is on that big hill. That hill is the fault scarp for the, I think it was the Raymond Fault. Generally speaking, a fault scarp is sort of, it's the vertical, what we'd say is the vertical displacement, the vertical offset of a fault. It's small here. It's a good 30 feet. But given the lateral, the side-to-side offset, which is way more dramatic, what we're seeing here is that evidence that the San Andreas Fault is mostly movement in a lateral motion with a very small amount of vertical motion. The last time that the southern section of the San Andreas Fault ruptured was in 1857. That's what we call the Fort Tejon quake. It actually ruptured much further south, and the only place that was settled at the time was Fort Tejon, so that's where we said it started at. So that was the last time that the southern section ruptured. We had the 1906 quake up in San Francisco, was the northern section. Central section creeps, totally different bag of beans. That's not a saying. Anyway, so we have the creek coming up, let's see, coming up that way, and then it cuts across. You can follow that little line, the little line of grass right here, and goes down here. So we've got across, up again. So this is the offset that was from the 1857 quake. Now, how do we know that this was from the 1857 quake? There's a couple ways, and the biggest one. And then I decided to stop recording. Okay, what I would have said is that the way that we know that this particular channel was offset during the 1857 quake is because of the lateral movement on that channel. So, like I said, it's about 10 feet from the head of the channel to where the offset part is. We know that when the San Andreas Fault ruptures, it moves about 10 feet laterally, 10 to 20 feet. Because this section, this little creek or this channel, has only undergone about 10 feet of lateral displacement, we can assume it's only experienced one earthquake. That is, like, in comparison to something like Wallace Creek, which we were just looking at. Wallace Creek is about 430 feet of lateral offset. So we know it's undergone multiple earthquakes because you can't get 430 feet of displacement in one earthquake. So we know that's over thousands of years. There we go. All right, so we're coming up again on another one of those little offset bitty creeks. Again, you see here, following the path of the shrubbery is really helpful in this case. So you've got that, we cut across, and then you can see a little signpost there, which took me a really long, embarrassingly long time to find, but then you come up here and this is again that creek head. So we're again seeing that offset from the 1857 quake. All right, so what we've got here, it doesn't look very dramatic, but it has a very dramatic name. Right, Kit? So this is a beheaded channel. This is the bottom part of the channel, right? We've seen a bunch of these at this point. You're looking for the offset. This would be where the offset is, and then theoretically, somewhere on that hill, there should be a creek head. There should be the top of the creek that would feed this. But instead of having that channel, there's, as you can see, nothing. So that means that I'm just amusing myself, don't mind me. That means that somewhere in that direction, further along, is where the creek, the rest of that channel would be, but we don't know exactly where that is, or I don't know exactly where that is anyway. And so as a result, because there's no more channel to feed this one, we call this a beheaded channel. I will explain how that happens as well, because I'm not good with doing stuff in my head visually, so I often have to I like doing really terrible drawings, so I'm going to do a really terrible drawing, probably when I get home, to explain how this works. Real quick, beheaded stream channel. So this is, let's say, the channel that we're working with. Split in the paper is going to be our San Andreas Fault. Channel is flowing normally, and then an earthquake happens. Oh no. So then the water starts flowing like that. So it creates that good zag shape that we saw at Wallace Creek. Probably because it's most convenient, water likes easy. But you know what's even easier than taking this long circuitous route is making a straight line. And so over time, the water will start to flow in a straight line again and stop flowing to this part of the creek. What'll then happen is that there'll be another earthquake, and this process will repeat where we get that zag shape. But now, so like I said, in this part of the zag is still getting water. This part over here isn't getting water anymore. It's now dried up. That becomes a beheaded channel. Why does Wallace Creek matter? Wallace Creek tells us a lot of really important information about the San Andreas Fault. Offset channels in general, or offset lines, any number of offsets can tell us really important things about the fault. First of all, like I said, it tells us just how far, how much lateral displacement we're dealing with. So knowing that we can measure from one end of the displaced creek to the other, all of a sudden we've got 10 feet. If we can then go from there and figure that that is kind of what the average displacement is, especially if we can then track it through time. Second thing, it holds a paleoseismic record. So when you have something like Wallace Creek where it's 430 feet of offset, we can do a couple things. We can carbon date and then also use the distance itself to figure out how many times there's been an earthquake. And then when you do that, when you figure out how many times there's been an earthquake and you know how long this creek has been around. So if the creek has been around 4,000 years, and if there's been 10 earthquakes, you divide 4,000 by 10. In this case, those are just numbers off the top of my head. What you end up getting is the rate of recurrence. So the rate of recurrence is what's the year interval between earthquakes. For the San Andreas Fault, we found it's about 150 to 200 years. That is massively helpful because while we can't predict earthquakes, and that's really important to mention, we cannot predict earthquakes, we can kind of forecast them. So you can say within a window it's gonna happen, which is why you always hear Los Angeles and California, Southern California, is overdue for an earthquake because the last one was 1857, the last one on the southern section was 1680, so we are well within that 200-year range that there should be a recurrence. The last thing that it tells us is the rate of plate movement. So again, you take a look at how long this has been interacting, you take a look at the distance, you divide the distance divided by time, and you get feet, inches, meters per year. That tells us how fast the plates are moving, or it did before we had GPS data. Now that we have GPS data, we can kind of make sure, and it turns out that math checks out. So that is why Wallace Creek matters. One more thing, just real quick. I'm not wearing a mask in the videos because when I say there was no one around me, there was literally nobody around me I was the only car in the parking lot. The only time that there were people was that part where there was that little small people in the distance. But it's important when we are out in our public spaces, especially in our kind of shared national monuments, shared national parks, things like that. Even though we're outside, please keep your masks on. Just be mindful of the people around you. It is important. Anyway, thanks for watching, and I will see you guys whenever I decide to start doing my rock collection videos again. Thanks.